together, we will be presenting the vehicle thermal management in Star CCM Plus to achieve fast, reliable, and realistic CFD results. For any automotive industry, it's critical to ensure that the thermal safety of all the components of the vehicle in order to prevent melting and burning of components, engine overheating, or component fatigue. With introduction of the electrical vehicle technology, as well as higher powered and efficient engines, maintaining a safer operating temperature in the underhood environment becomes increasingly difficult. But also industries today are aiming for shorter design cycles and reducing physical validations to save time and the cost involved. One answer to all these complex challenges is simulations. However, simulations has its own challenges. In today's in today's presentation, we are going to focus on the challenges faced by simulations of VTM systems and how Star CCM Plus particularly can resolve them. Let us start with the main challenges faced by VTM simulation engineers. One of the most obvious challenge in the vehicle thermal management is that we need to handle thousands of parts, and the process can be confusing, repetitive, and difficult to do. This results in a workflow that is inefficient. Nowadays, it is very common for VTM engineers to use multiple softwares to get results from a single simulation file. There will be a given tool for CAD cleanup, another for meshing, solving, and another for post-processing. Such tasks result in a disconnected process so that any change in the CAD, for example, will not relate to the changes in the mesh and the boundary condition, and so on. This often leads to organizations developing their own scripts, which are generally valid for a given release. The scripting is not limited to just processes, but also multiphysics simulations. For example, commonly in simulation for transient, we have a separate tool for CFD and another tool for thermal simulation, and that both of them need to be connected, often via file transfer. This leads to inefficiencies and slow solve times. As seen in the previous hands-on simulation series, any disconnected process limits the engineers to analyze a given problem and hinder optimization. Essentially, if I were to sum up these challenges, due to size and complexity of the models, VTM engineers spend more time to build the CFD models than analyzing the results. Exploring the design space is not even considered. As we have seen through the previous sessions, Star CCM Plus is designed to counter this. The philosophy here is to discover better designs faster. The agenda for today's session is going to be as follows. To begin with, we are going to start with the simulation of a vehicle using the template-based approach. We are going to have a look at the design optimization using IDE, that is Intelligent Design Space Exploration. There will be a live demo on the surface wrapping feature, which is a tool set that reduces the time for geometry preparation and repair. And at last, we will have an overview of VTM simulation by Daniel Steen, who is an expert from this particular domain, and he is from Siemens. So let's begin. We have seen in the previous session that Star CCM Plus has been designed from ground up to basically provide a single environment to perform the simulations in an automated manner that has rapid turnaround time and that allows you to get results quickly and lets you spend more time analyzing the results. However, we have yet to tackle the problems with very complicated system of geometry and subsystems such as those found in the VTM analysis. It is important that we model these systems to get realistic results that can give us information about the complex systems and the physics involved. For these reasons, it is very common that large automotive firms use Star CCM Plus for their VTM analysis. And let's see how that is particularly done. In the traditional workflow, CAE teams download the data from the CAD system. The data is then taken to the third-party preparation tool, where typically surfaces are simplified and even components such as bolt, nuts, and clips are removed. To complete this for a full vehicle, this manual process of CAD to CAE preparation takes around 7 weeks. With this kind of preparation, traditionally you would have a CFD model and another model for the thermal solver. Hopefully both using the same surface if possible. Clients running long drive cycles need to send results from the CFD solver to the thermal solver. This data transfer is typically done only once or twice for a given simulation since it is time consuming. Once done, a different tool is used for post-processing as you require information from two different solvers, and this makes it difficult to analyze the results. Now let's see how that is done in Star CCM Plus to have a quick turnaround time. As seen in the As seen in the hands-on simulation sessions, we can make use of the predefined template that stores the process from CAD to CAE. All we need to do is tag a different material or assemblies so filters can automatically put these into the new model. Depending on the complexity of the geometry involved, the entire process from CAD to simulation will take days and not weeks as seen in the traditional method. With Star CCM Plus's integrated multiphysics solver, you can run both thermal and flow simulations and no file transfer required, making transient conjugate heat transfer simulations computationally inexpensive. In addition, using the built-in post-processor, you can analyze all forms of heat transfer, that is conduction, convection, radiation, together, giving you better insight on what actually is causing the particular part to overheat. All in all, we have a great turnaround time with Star CCM Plus, and the reason hinges on three different pillars, and let's go ahead and see what they are. To start off with, the car is an extremely complicated device. Let's start with the geometry, which is ideal for CAE. It's a mix and match of different parts. Out of the collection of parts, how do you determine what the materials are? How do you identify the fluid domains? How do you, once you have the parts, how do you define the boundary conditions for those components? How do you identify what is the coolant loop and how the fan is set up? And this is something that we are trying to design with Star CCM Plus from ground up using the template-based model to provide you with a more automated approach to answer these questions by just importing the CAD that comes out of your PLM system or any other data management system into the CAE analysis. We are going to look at this and see how it looks like in the Star CCM Plus. So let us jump to the tool. So this is the GUI of what Star CCM Plus looks like. Just give me a second. Let's go ahead and import the CAD. So the first thing is to open what we call the template-based model. This is what we will be sharing the files later on. This is what the template file looks like. So once the template-based model has been imported, what you can see is that everything is pre-configured in this particular system. Let's give it a couple of seconds. Yeah. The template model has been imported and it has pre-configured data, as I said. In the previous sessions, you had a look at how to create the template-based model where Yafis described the methodologies of various advantages of having the template-based model. So let us have a look at what the template-based model for VTM vehicle thermal management simulation looks like. We have all the operations over here, which you can see on the screen. There are a couple of operations which are present right from creating the wind tunnel. We have operations to extract the fluid volume right from the fan region, the exhaust fluids. We have wrapper and automated mesh for the solids. We have wrapper and automated mesh for the fluid region as well. So solids and fluids. So there will be a conjugate heat transfer analysis. We have the MRF zone. So we have operations which are created pretty much for every single thing which is required to run the simulation in an VTM analysis. Secondly, we have the continuas which are present over here. We have air for modeling the ambient region as well as the underhood environment. We have coolant, which is used water, which we have modeled the coolant as water for this particular case because the radiator is modeled as a dual stream heat exchanger. And then we have solids. So in solids, we have different material properties defined depending upon the type of material which you would like to place for your particular solid. So it's easier for you to go ahead and select these for conjugate heat transfer analysis. So going ahead, we have the regions as well. We have a region for the ambient, that includes the underhood environment. We have the condenser core, which is modeled as a porous region. We have the MRF zone, which is the moving reference frame for the fan, which sucks in the air from the grill and blows it over the engine. We have the radiator air core. So the radiator over here is modeled as a dual stream heat exchanger. So we have the radiator core for both air and the fluid as well. And we have a region created for the solids. I will be going in detail for each of these sections when we reach the multiphysics tab. Other than this, let's go ahead and see what data do we have for post-processing. We have the plots which are pre-created. Once you run the simulation, once you mesh and run the simulation, you have the plots which are ready over here. We have a whole set of plots. So we have residuals, we have plots for the cooling packages, that is air mass flow rate and outlet temperature. So you can make sure that your model has been well converged over here. Other than that, we have scenes for post-processing. There are two kinds of scenes over here which are pre-created. That is pre-processing and post-processing. In the pre-processing scenes, we have solids, we have anything related to the wrap surface, we have volume mesh, and you're going to see as we go ahead during this tutorial, you're going to see the advantages of having all these scenes. And in the post-processing scene, you have scene created for almost everything. You have scenes for the heat exchangers, that is the air side and the coolant side as well. You have the solid temperatures, you have the surface touch temperatures. So let us go ahead and begin. So I'm going to go ahead and open the solid scene, but right now there is no information over here because we have not yet imported the CAD. The next step for us is to go ahead and import the CAD. So So to import the CAD, it's going to be a PLM XML file. So we will have to go ahead and uh, activate. So we cannot see the PLM XML button over here. So we will have to go ahead and bring this. So I will show it to you as many of you may not find it the first time. So you go to Tools, Options, and you have the Import PLM XML over here. So I'm going to just click it and drag it and place it somewhere here. And we can go ahead and import the complete CAD using this. So let me open another file in which the complete CAD has been imported. In this particular file, you have the CAD which is imported and it's been placed in main. So in the template sim file, you will have something called as a main geometry. And once you import the complete CAD, you are going to drag it and drop it and place it in the complete in main. So once you have that, what you can see is in the scenes, you can go to pre and open the solid scene. And once you open the solid scene, you can see that the entire vehicle appears. So since it is graphically a little bit heavy, so it's going to take a couple of seconds to open. So yes, we have the entire CAD geometry which is imported. During the previous session, Yafas showed us the importance of tagging a particular part to assign the properties to it. So let us go ahead and create one such tag to one of these parts. So for example, let us go ahead and select the body front. Let me show you how it's done. Yafas did mention it in the previous sessions, but let's have a repeated session where we can just show you how to tag and how easy it is to assign material properties to the particular component. So right click on the particular part, click on tags, add an existing tag. So over here, you have a whole set of tags which are present over here. Right from the boundary condition, we have the continuum, that is the continuum, maybe a coolant fluid or the solid. We have the tags for domains so that it can be maybe a heat exchanger, maybe a fan region, maybe a left exhaust fluid, right exhaust fluid, or the radiator. Other than that, in the tags, we also have pre-created tags for material properties. As I told you, as I showed you in the continue, we have 4 material properties defined over here, and also mesh refinements. So you can specify the mesh, the refinement of the mesh which you would like. So if it's fine, if it's a heat shield or a thin component, and if you would like a fine mesh, you can go ahead and select that over here. So the next thing to do is for us to tag this body front part. So I'm going to specify it as solid and assign material as plastic to it and click on OK. And when you do this, you can see that this particular part has been appears as a solid part over here, and it has been tagged. So using this method, we can see that in the template sim file, it recognizes that this part needs to be modeled as a solid with this particular mesh properties. And it is by this mechanism that we, the analyst, can identify the context of these components, and we are we can quickly walk through an entire complex set of geometry and define the conditions. So also over here, some of the it's going to take us sufficiently larger amount of time to tag all these parts. So we have already tagged all the engine components over here, including the heat shields and the plastic components, and the model is set up for us. Using the tag method or the template-based sim file, it does save us a lot of time. It maintains consistency and avoids a potential to do mistakes in setting up a particular model or a complex problem like this. So let us jump back to the presentation. We saw that a template-based approach where we took the raw geometry, gave it a context, and now we can build a simulation file out of it. And we did this fairly quickly. However, it was not a fully automatic process. We still had to apply the tags manually. However, we can speed up the process of adding material data if we take advantage of the PLM platform like Teamcenter, where the metadata can actually travel with the geometry right from the CAD design stage. Metadata can be managed upstream to help further automate the setup within Star CCM+. Teamcenter is a tool that can be leveraged to help achieve a greater degree of automation, speed, and reliability in setting up simulations. We have the geometry brought in. We have defined the context. At some point, we actually need to define the physics and simulate these physics for the vehicle thermal management application. And this can be quite challenging. You have an underhood environment. You have cooling systems like the radiator with a single and maybe a dual stream. We have moving parts for the fan and the wheels. We have external aerodynamic flow. And we are basically trying to capture all these physics in a single simulation file. And we are doing this to produce a final temperature distribution on the vehicle. And let's have a look at this in the tool itself. So we did go through the regions a few minutes ago, but let's have a look at this in a more detailed manner. So we have the ambient fluid for the entire ambient region. Then we have the condenser core, which is present over here. So the condenser core is modeled as a porous region. Give it a every time we click on a component, it's going to highlight that particular component on the screen. And this can sometimes, if the part is heavy, it can take a couple of seconds. Okay. Yep. It's a little stuck. Just give it a couple of seconds. Yeah. So what you can see on the screen over here is the condenser region, which is modeled as a porous region. There are two options over here. Depending upon the continua that you select, you have the porous region as well as the fluid region. For the condenser, it's modeled as a porous region. The condenser has both an inlet interface to the ambient air and also an outlet interface over here. Other than that, the walls of the condenser, the edges of the condenser are modeled as walls. So let's have a look at how the condenser is modeled. So the condenser has a heat exchanger total energy rate of 9 kilowatt is specified to the condenser. And also, since it's a porous medium, we have both the porous inertial resistance and the porous viscous resistance. So in the porous inertial resistance, we have the axial component defined over here, as well as in the porous viscous resistance, we have both the axial and the transverse component defined. This is how we have modeled this particular heat exchanger as a porous medium. Other than this, we have another heat exchanger, that is the radiator. It is the bigger heat exchanger. This is the radiator air core. So the radiator is modeled as a dual stream heat exchanger. So we have the air core and the coolant core. In the coolant core, this is what you can see on the screen is the coolant core. We have the coolant holding tanks as well, which we have modeled over here, as you can see. The coolant holding tanks we specify a mass flow rate. We both have the inlet over here, which you can see. If I highlight this particularly, you can see on the screen that there is both an inlet and an outlet for the coolant. So this is how we model the radiator, particularly as a dual stream heat exchanger. Other than this, we have modeled the fan MRF as a MRF zone. So We have the fan over here. As you can see, it's modeled as MRF zone and it's been meshed as well. So if I look at the default boundary, this is the fan, this is what the fan looks like, and it's been given motion. So how do we specify the motion? Over here, we have something called motion specification, and in the reference frame, we have selected reference frame for fan rotation. So if we go ahead and see, so let's go to representation. It's in the tools. There's something which we have called the reference frame. So we have the reference frame for fan rotation. It's been grayed out because it's frozen over here, but we have a rotation rate of the fan for 418 radians per second, as well as the laboratory, the coordinate system is the reference frame for this particular fan reference frame is specified as fan. And this is where you define the coordinate system. You can see the fan coordinate system and it rotates about the Z axis. So this is particularly how you define rotation for the fan. So, and also we have also modeled, just like we modeled porous region for the um, for the heat exchangers in the front, we have the catalytic converters over here, which, and these two, the right and the left catalytic converters, are modeled as modeled are these particular ones are modeled as porous regions as well. So once we have all of these, the next step would be to mesh the simulation and run it. So this particular file would take around it would take around 6 hours to mesh and another 4 to 5 hours to run the simulation. So this particular file has already been meshed and saved. So let me show you the meshes in the pre-created scenes which are already ready. So we have different kinds of representations over here. Let's go ahead and open the mesh section. So this is going to be a mesh, a section in the x-axis, which slices through the center of the vehicle, showing us the mesh representation both for the solids and the fluids as well. So you can see that ambient fluid domain is modeled as a trimmed cell measure, and you can see the various volume refinement boxes which are present. If I zoom in over here, you can see the different components. You can see the heat exchangers, that is the condenser and the radiator, which are modeled again as trimmed cell measure. But the fan zone over here particularly is modeled as a polyhedral mesh. And also the engine, the solid parts of the engine, these particulars, the engine is modeled as a polyhedral element. So you can see that the entire vehicle has been modeled over here. The entire underhood environment of the vehicle has been modeled, including the axle, the wheels, and all the heat exchangers, including the engine and the transmission. So the next thing which I would like to show you is which I can show you is the internal fluids that we have extracted. And all of these internal fluids are extracted using the operations which you already have. You don't have to go ahead and create any other operation to extract these particular fluids. We have the coolant holding tanks, we have the radiator and the condenser, the MRF region over here. Also, the exhaust fluid is the entire exhaust line is modeled for conjugate heat transfer analysis. So you're going to specify the mass flow rate at the inlet of the exhaust manifold over here, and it's going to go all the way to the rear tail pipe of the vehicle. And this particular exhaust is modeled to model both conduction, convection, and radiation, to model all the modes of heat transfer. So we had a look at the and the mesh as well. So now let's start looking at the results. Before we look at the results, we have run this simulation. So let's have a look at the plots to understand if this particular um, if this particular solution has been converged. So I'm going to go ahead and open the residuals. You can see that this simulation is run for 2000 iterations entirely, and the solution is converged. There is a fair amount of convergence over here, so we can go ahead and confirm that when we look at the coolant mass flow rate, the heat exchanger air mass flow rate, both for the condenser and the radiator. So now that we are convinced that the solution has been converged, we can look at the pre-created scenes. All you need to do is go ahead and open these scenes. So you can look at the air temperature of the heat exchangers. So you can see that the air temperature of the heat exchanger as it enters the vehicle, it's at ambient temperature, but whereas it grabs heat from the dual stream heat exchanger of the radiator, which has been modeled, and that we can see in the radiator. On the left hand side, you can see the air temperature of the radiator core, and on the right hand side, you can see the coolant temperature. So you can see that the coolant enters the radiator, which is hot. The temperature is pretty high, and it exits the radiator at a lower temperature, maybe 7 to 8 degrees lower, depending upon the mass flow rate that we have. So since we modeled the exhaust fluid particularly, we can have a look at the exhaust gas fluid temperature. You can see that the temperature is pretty high as it exits the engine. It moves all the way through the catalytic converters and then exits to the tailpipe. One of the most important things which we would like to see would be the solid temperatures. And this would be for all the parts that you have modeled as solids. So let's have a look in detail. Let's give it a second because it's an entire vehicle. So on the screen, you can see all the solids which we had modeled have a surface solid temperature to it. You can see the temperature of the heat shields. You can have a look at the exhaust pipe as well, because the scale of the temperature is limited. You can see the entire exhaust pipe is red over here. So let us some of the parts of the vehicle have not been modeled as a solid. They have been modeled as adiabatic walls, but still we can have a look at the temperature of those particular walls as well. This would be the surface touch temperature of the entire vehicle. Unlike in the previous scene, we saw the temperature of the solids which we had particularly modeled. Yep, so this is the surface touch temperature of the vehicle. You can see on the lower side that this entire exhaust line is hot, and as you can see over here, it might grab your attention that the bumper, which is not modeled currently as a solid, but you can see that the tailpipe is going to heat the bumper significantly. The temperature is going to be, because the heat shield ends way behind, the tailpipe is going to heat this particular bumper, and the bumper limit, the critical temperature for a bumper is usually 110 to 120 degrees C, but over here it is way higher. So our goal would be, the easiest thing for us would be to model this bumper as a solid firstly, and also the second thing would be for us would be to extend the heat shield all the way till the end of the tailpipe. So what I'm going to do is, let me show you how we can go ahead and model the bumper as a solid. All you need to do is double click on this particular part. So it takes us to the model under panel, or the bumper, or the plastic component. So we're going to right click, go to tags, add existing. So it's going to be a solid, and we model it as a plastic bumper, and click on OK. And this is how you can go ahead and assign tag and easily specify maybe the mesh condition, or the solid properties, or the boundary conditions for a particular part in the vehicle. So let's get back to the presentation now. The idea with a co-simulation here is that we can do it in one single simulation file. You need to submit only one file to the cluster. You have to work with only one file. You don't have the trouble to get two different simulations files talking to each other. This is another example of the kind of multiphysics integration that we integrate in Simcenter Star CCM Plus. To conclude, we have just modeled all of this in a steady state thermal model, but we can go further than this and simulate transient models covering all discipline and physics. It is possible to enable long thermal drive cycle and soak simulations with single tool for both thermal and fluid regions. We can also capture harsh driving conditions like wind, snow, or rain because Star CCM Plus can simulate all these multi-physics conditions. We have all this ability to handle the data to build these complex simulation, but none of that matters if it takes forever to complete the simulation and to obtain the solution. Once the CAD is ready from the design team, The first underhood simulation setup takes significant time, and very less time is spent on offering design recommendations before the prototype stage. This results in us having many serious problems in the prototype stage, and that's what we are really trying to address with Simcenter Star CCM Plus. The CAE model can be built a lot quicker, design iterations can be performed in the same time span, and prototypes can be built taking into consideration all these aspects, which would result in fewer problems. Let us have a look at one such design problem. Let us consider the same example of the plastic bumper overheated, which we saw a few seconds ago. The traditional method for a design would be to import the geometry of the new part, assign mesh and boundary conditions to the part, mesh the full domain, and then run the solution. This would take a significantly large amount of time to accomplish. What if I told you we can cut down this time by 50% compared to the traditional method? And this is what I'm going to show you now. Local meshing speeds up the re-execution of the surface remesher after local changes are made to the input geometry or the mesh settings. With this feature, Star CCM Plus only remeshes surfaces which is defined within a defined location and leaves other surfaces unchanged. We have a total mesh count of 18 million, and traditionally this would take 7 to 8 hours to mesh both the solid and the fluid domain. We can cut down this time significantly to 2 hours by using the feature of local wrap and remesh in Star CCM Plus. Let us jump back to the tool and understand how this is done. Let's go ahead and open a separate sim file with the same geometry. We can go and open the solid scene of the exhaust lines and the engine which is present. Let me go ahead and hide the transparency of the vehicle geometry for us to easily work on the other parts. Now our first goal is to go ahead and replace the heat shield, because the heat shields were not a proper design and they were burning the bumpers. So what I'm going to do is I'm going to show you both the muffler heat shields over here. Let's look at it in the top view. You can see that it's not covering the tailpipe fully. So I'm going to double click on this particular part and it's going to take me to that particular part in the tree. So this is the left muffler heat shield, which I'm going to highlight, and the other side, it has the right muffler heat shield. So we'll go ahead, right click and replace both these parts. So the first thing is go ahead on the left muffler heat shield. We're going to right click on the replace part. And here, one thing which I want to stress is that it's important that you maintain the existing part name both on the part level and the leaf level has to be same. The name has to be the same with the new CAD that you're importing, because the next when we select the left muffler heat shield, you get two options: either match by surface ID or by name. So we're going to use the name and click on OK. And when this happens, you can automatically see on the scene that the heat shield has been updated. Similarly, we'll perform the same task for the right heat shield. Replace part, select the right heat shield, match surfaces by name, and the scene is updated. So now our job of importing the heat shields has been done. So now the question comes, do we have to redefine the mesh settings or the boundary conditions or any other properties or the material properties of this component? My answer is no. So you can see that we had tagged the part previously, so these tags are maintained still. You can see that the solid is continuum, material is aluminum, and mesh refinement, since it's a thin component, is fine, and these are maintained. So you don't have to go ahead and assign any of these over and over again, because we replaced that particular part. It's maintained for both the right and the left muffler heat shield, so the tags are retained. So let's get back to the operations and execute the first operation. We need to remember that in Star CCM Plus, the operations, it goes in a chronological manner. So it starts from the top and then comes one by one. You have to execute them. So let's go ahead and execute the first operation of creating the wind tunnel quickly. It's just going to take a second. That's done. So the our next interest would be to create what we call, so we have to specify the extent to which we want to have the local wrap or the local mesh in. So we are going to create a domain around the left and the right muffler heat shield, and that's what we are going to do. For that, we are going to go ahead and create what we call an offset. So in Star CCM, we have three operations. but the offset operation is present in the surface preparation. So we are going to select the heat shields, and we want to basically inflate the heat shield and create a region around it. In the exhaust system, we have both the right and the left muffler heat shield. Click OK. And also we need to define the extent to which you want to inflate this particular heat shield. That's going to be 0.1 meter. I also want to remind you guys that it happens in a chronological order. So what we need to do over here is it's important that we reorder this and place the offset or the localized region before we wrap or do the automated mesh. So basically we create the offset, we define that, okay, you're going to mesh in this particular domain. And so this particular operation has to be present before the solid surface wrapper or the automated mesh. So I'm going to right click on operations and reorder it and place it before the surface wrapper or the automated mesh. And I'm going to right click, execute. So the offset body is now being created. So let's have a look at it in the part tree. There is a part which has been created when we executed this particular operation. Let me highlight it. So this is the domain in which the local remesh or the wrap is going to happen. So now we have defined the local zone within which we want to create the offset. The next step is let's go ahead and see the wrapped representation. So let me change the representation to wrap, and you can see that in the wrapped representation, it's still the old heat shield because we have not yet wrapped the geometry with the new heat shield. So that's what we are going to do today. So you can see that the heat shield is still the old one. So let's go to the operations of solid wrap. Simulation, solid surface wrapper. And over here, we have to tick what we call the perform local surface wrapping. And this will enable the local wrapping. And after that, the second step is to go create a local extent within which we want the wrap to occur. So we'll right click over here, new volume extent. And this is the extent within which the wrap will occur. And that is defined by the offset body, which we just created. So in parts, we will select the offset domain. Click on OK. So we just right click. This similar kind of operation will have to be done for the automated mesh, but we will do it later. Let's get back to the surface wrapper itself and right click and execute. So we need to remember over here that the local surface wrapping happens in serial, and we can execute this particular operation. So what is happening right now on the screen, as you can see, 23 out of 86. So what the software is doing is it is looking for each part and checking if that particular part is present in the local domain that we have defined. If yes, if it is present in the local domain, then and only then it will wrap the particular part. Otherwise, it wraps every body present in the solid domain. So what happens is if we had wrapped all the solids, it would have taken us 15 to 20 minutes to complete. But over here, since we have local wrapped, it is almost complete right now. It just takes a minute or two to finish. So just to reiterate the steps, we created an offset and then we tick marked the local surface wrapping, and then we created a volume extent and specified the offset in that particular local extent. So the surface wrap is almost completed. Yeah, it's finished. Now you can see suddenly the scene got updated and the surface wrapper, because we had the representation as surface wrap, the scene got updated automatically with the wrapped representation with the updated heat shield. So the next step is to do the similar exercise for the automated mesh. I'm going to go ahead and tick perform local surface meshing, create a volume extent, and in the volume extent define, it's the same task that we performed for the local wrap. It's the same task. We specify offset, click OK. and execute. Same thing, let's go ahead and change it to serial and execute the operation. So this is going to take a little time, and once it's completed, it's going to take 15 to 20 minutes to complete. I have a file which is already wrapped, so let's have a look at it. So let's go to the representation of surface mesh. The mesh is completed for the solid, so let's have a look at the surface mesh. So you can see once it's updated, once the scene is updated, you can see that in Star CCM Plus, the surface mesh is tetrahedral, whereas if we specify the volume mesh to be polyhedral, the surface, it's going to grow from the surface, that is, it is going to join the tetrahedral elements to create polyhedral elements. So I will go ahead and change the representation to volume mesh itself. So let's have a look at it. It is going to be polyhedral elements, and because it's a thin component over here, the heat shield is a thin component, we have modeled it as a thin mesher. So you can, once it's updated, you can see that it creates a really good mesh. So you can see polyhedral elements over here, but they are stacked up in layers. So you can go ahead and increase the number of layers or change it if you wish to. Similarly, we can perform the wrap and volume mesh for the fluid domain as well. We created the localized wrap and the remesh for the solid domain. But similarly, it can be done for the fluid domain, for the entire fluid domain. Typically, to wrap and mesh the fluid domain, it takes 7 hours. But with localized remeshing, just like I showed you, it takes 1 hour to complete, and I have tried it on my own. And that is a huge reduction in time when you're performing design iterations. The solution needs, so the next step would be to run the simulation with the updated heat shield. The solution need not be erased from the base file. We can continue solving the existing results and with the updated heat shield, and the results will converge a lot quicker to take into consideration the new heat shield in the model. So let us open a file which is already converged. So you can see that all the bumper is modeled over here as a solid. We have all the operations as well executed. So the model has been meshed and run. So let's have a look at the residuals. So you can see, let me open the residuals. So you can see on the screen that there is a spike. That spike is where we replaced the heat shield, presented a new heat shield, and you can basically see that just in a couple of hundred or maybe 500 iteration, the solution has converged. So let's also have a look just to confirm for the air mass flow if it's converged. Yes, it has been converged because there is no effect of the heat shield, which is at the back of the vehicle on the front side of the car. So we had a look at, now let us have a look at the bumper temperature, which was the most important thing which we wanted to see. The bumper was burnt in our previous simulation, but now we have updated the heat shield. So I'm going to go ahead and open the solid temperature in a pre-created scene. Let us rotate the vehicle and have a look at the bumper. You can see that the heat shield is extended. We have, and also the bumper temperature is much, much lower than the last time it was. So it's safe to say that the bumper is safe right now. So using the local surface wrap and remesh, it is very easy to mesh and run the simulation and have the results as soon as possible. Now let us have a look at the solids as well and have the temperature and the solids next to each other. Yeah, I have placed it now. So now you can see that the solid is present on one screen with linked view. So if I zoom in one of the screens, it's going to zoom in the other scene as well. So this is a very important feature which can be used for post processing or to present results to your customers or your clients. You can have multiple scenes in the same window, in the same orientation, and present the results in a much better format. So now we saw the local meshing and wrapping and how we can achieve we can achieve a significant reduction in the time in running design iterations. This is also another example of the accuracy of Star CCM Plus being realized by one of our key customers. One common test for vehicle thermal management is the low speed uphill drive trailer tow test. We are looking at the peak temperature versus time. During the transient case, we can pick up critical zones when and where they occur and which components exceed their critical max operating temperatures. While tests can provide around 300 points in simulation, we can have unlimited number of probes to record the data and understand the behavior of components to various load conditions. Just to give you an idea of what this would look like in the real world situation, as you have seen in Star CCM Plus, a lot of the process from part organization to post-processing has been automated to reduce turnaround time. Depending on the complexity of the geometry, CAD to solution, this would take a couple of days as opposed to weeks and maybe months with other tools. Once the model is completed, the design changes can be incorporated at a much faster rate using the pipeline workflow, as you don't have to rebuild the operations and settings from scratch. And this quick turnaround time is true for any industry and not only limited to automotive. The template-based approach and pipeline workflow can be leveraged by everyone, be it aerospace, HVAC, oil and gas, or any other industry which has thousands of parts and complex physics to simulate. The next, the next most important part of the simulation is to find better designs faster. This pipelined automated workflow in Star CCM Plus enables easier design changes all the way from component swap to looking at thousands of different scenarios and trade-off solutions. You can take advantage of the multidisciplinary optimization tool HEATS, which can be a standalone, or we can take advantage of the design manager within Star CCM Plus to do multi-objective optimizations or design of experiment studies. For instance, this automotive company was trying to reduce the vehicle drag, but we also wanted to increase the mass flow rate through the heat exchangers during the hill climb. We have the CAD for the fan grill and a couple of other parameters. And here we are simply going to let Star CCM Plus and Heats modify the geometry to identify the best compromise to reduce the vehicle drag involving the improving the radiator performance. Heats uses algorithm Sherpa. It's actually going through and looking at the performance of the fluid design and tweaking and adjusting it as it goes using a combination of different optimization routines, including genetic algorithm. Using this, the company developed a new design that resulted in a drag reduction and increased radiator performance. And we were basically able to run over 100 different designs in 6 days using Star CCM Plus to achieve 5.4 reduction in drag, 5.4% reduction in drag, and 11% reduction in the radiator output air temperature. At the end, let me show you one of the important geometry preparation feature inside Star CCM Plus, which you can go ahead and use. The surface wrapper can be used to provide a closed, non-intersecting surface when starting from bad quality CAD. Surface wrapper is an excellent feature in Star CCM Plus, which can be used particularly during two kinds of instances. Firstly, when you have a poor quality CAD. By poor quality CAD, I mean multiple intersecting parts, missing data from the in maybe holes and gaps, surface mismatches, duplicate and internal surfaces, and overly complex geometry. Once we wrap the solid geometry, we can obtain a clean CAD and move ahead with meshing. The second use of surface wrap can be, it can prove challenging to extract the fluid volume from a poor quality CAD with maybe holes or gaps or mismatches. The surface wrapper helps us overcome these problems by neglecting small surface deformations and producing a smooth fluid volume. Putting it in simple terms, let us take this example of the stack of boxes which has been shrink wrapped. We have boxes with gaps in between. Some of the boxes are protruding out, some have holes and are damaged. On putting a plastic wrap on the surface, all the deformities have been ignored to create a watertight geometry, and that's our end goal. Now let us look at the wrap operation of an exhaust assembly. We have the same exhaust assembly parts on the screen consisting of 10 plus parts. Before we move ahead with the mesh operations, we would like to get rid of all these deformities which you can see on the screen, and that can be easily achieved using a surface wrap. Let us have a look at this particular feature in Star CCM Plus by working on a live example. So we have the same exhaust which I showed you. There are three scenes which are pre-created. We have the scene for the original CAD. which is this particular scene in which the CAD has been dropped. We have a solid wrap scene, which is empty, which we will drop it later, which will drop the part later. And we have another one for the left exhaust fluid volume. What we have is an exhaust assembly. So let me open it and show it to you. There are around 10 parts. And we might have a question, why do we wrap the surface? We have the catalytic converters. We have a couple of parts, the left manifold, and the question at the end arises, why do we have to wrap this particular surface? And that is what I would like to address first. So let us have a look at why do we do this. So I'm going to right click on the exhaust system, click on repair surface, and it's going to open the repair tab of Star CCM Plus. On the right hand corner, you can see these different colors which are present. We have a couple of thresholds which are there over here. We have pierced faces, we have face quality. So the pierced face is something, if a surface is intersecting another surface, that is what pierced face is. We have the free edges. A free edge is nothing but a overhanging edge which is not connected to any other edge. We also have the non-manifold edges. If an edge is connected to two or more surfaces, then it's a problem, and that's a non-manifold edge. And we have the non-manifold vertices. So I'm going to go ahead and click on execute, and this way we can check the amount of intersections that we have. We can see that we have plenty of intersections over here. We have around 4,000 intersections and maybe 400 to 500 free edges. So all these can create a serious problem for the meshing, or the automated surface mesh, or the volume mesh. So these can be, of course, these can be eliminated. These errors can be eliminated in the repair tool itself. We can go ahead and maybe inflate the layers, or we can repair all of these errors, but it would take significant time. So the easiest way to tackle these particular problems, these thousands of problems, is using the surface wrap. Using the wrap, it will take us just 1 or 2 minutes, but opposed to if we had sat and repaired this particular part, it would take me around 10 to 15 minutes. So let's go ahead and create an operation for the surface wrapper and select all the parts that is of the exhaust assembly. So right now what we are doing is we are solid wrapping the solids of the exhaust assembly. So I'm going to select all the solids which are present, not going to select the inlet and the outlet. That is not required right now. So the next step is, let's go ahead and open the default controls in the tree and specify a base size. Base size is the reference length for all relative size controls, and that's going to be 10 mm. We have the minimum surface size of 10% of the base size, that is 1 mm. We have the volume of interest over here. And this is something which is interesting, or which is important for us to understand in the wrapper feature. For example, let's start with the first one. We have the largest internal. So for example, if we were wrapping an entire car and our goal was to wrap the cabin itself, the inner cabin where the passengers sit, then it would be a largest internal, because the inner cabin is the largest volume present in the car. So at that particular point, if we were wrapping the cabin, we would select largest internal. The second one, which you can see, is external, which we will be selecting now because we want to wrap individual components which are solid geometries. The third one is a seed point. If you have disconnected parts and you want to extract the fluid volume out of it, um, for example, over here, we have disconnected fluid volumes. For example, we have the catalytic converters in between, and we have the exhaust fluid. So at this point, when you have disconnected fluids, you select the seed point and specify particular seed points when and where you would like to have the wrap to occur. So these are the volume of interest which we have. So for this particular geometry, we'll go ahead and select external and rename the operation. Just for clarity, let's go ahead and rename it to solid wrap. And also let us rename the resulting part, which you can see in the part tree, to solid wrap, also the same name. So I'm going to go ahead, right click and execute. So right now it's just going to take maybe 20 seconds to 30 seconds, as opposed to if I had repaired it, it would have taken me 10 to 15 minutes. So now the entire geometry is going to be wrapped, and next what we're going to do is we're going to drop the wrapped surface in another scene which we have already pre-created, 01, which is named 01 solid wrap. So the wrap is completed. Now let's see how the wrap looks like. I'm going to drag and drop it on the scene. So this, what you are seeing on the screen, is not going to be, this is not going to be the original CAD. It's the wrapped representation. So you can see that it is a pretty good conformity with the original CAD. You can see the entire wrap, this entire exhaust line has been rewrapped, and it's fairly good, I would say. So let's have a look at it entirely. So, but there might be some portions which get chewed up, and let me show you the original CAD first. You would be able to appreciate it more. So let me zoom in between the flange and the exhaust manifold. We can see a gap over here which is present. And maybe particularly I want to model this gap in detail. Even on the bottom side, we have this gap. But if we look at the wrap, it's been chewed up and I'm not happy about it. So at this point, what we are going to do is we are going to create something what we call the contact prevention. So we are going to create a contact prevention that is by right clicking new contact prevention. We have two options over here, a one group contact prevention set and a two group contact prevention set. Just like the name suggests, in one group you specify all the parts between which you want separation to happen in a single group. So it can be a little inefficient if you have hundreds or thousands of parts which are specified as contact preventions in the one group contact prevention. But in the two group contact prevention, what happens is you have two groups, and in the first group you may mention that, okay, let's select the manifold in one group and the flange in the other. So there is going to be contact prevention only between these two particular parts, and it can be a lot more efficient. But since we have only two parts with us, let us go ahead and specify one group contact prevention and specify the minimum size as 2 mm. So the minimum size is nothing but, so for example, any surface deformity or gap which is lesser than 2 mm is going to be ignored, and any surface greater than 2 mm is going to be captured with a lot more detail. So when we specify, let's specify it contact prevention between the flange and the manifold, and the solid wrap is dirty again. So let us go ahead, right click and execute the solid wrap. So at the end, what you can see, the representation on the screen is a solid wrap representation. So once this is completed, once the wrap is completed, what you can see on the screen is going to be the flange and the exhaust manifold are going to be two separate parts, and it is going to be modeled pretty accurately as compared to the original CAD. Let's give it a couple of seconds. So the next, okay, it's done. So let me zoom in and show you. The flange is separated from the exhaust manifold now. The gap has modeled between these two particular parts. So one question you might have particularly is, how different is the wrap from the original geometry? Like maybe in terms of millimeters or meters, how different is it? And that's what I'm going to show you now. We have a field function which we call the deviation root distance, which is present in tools field functions. And over here we have this field function, and over here we are going to specify the original CAD. In parts, let's go ahead and select the original CAD which we have. Click on OK. And we are going to go ahead and create a scalar scene to compare how different is the wrapped representation from the original CAD. The scalar field function is going to be the deviation root distance. Click on OK. Maybe I can turn this off. Let us leave it for now on auto range. And the next step is select the parts. And in the parts, we are going to specify the solid wrapped surface to compare it with the original CAD. So I'm going to select the solid wrap part and click on OK. So once this is completed, you can see on the screen a comparison of the distance between the solid wrap and the original CAD. And right now it's in meters, which I may not be happy about. So let's go ahead and change. It's too much to compare it in meters. So let's go ahead and change it to millimeters. And you can see that most of the geometry is within the limits. That is lesser than maybe 1 mm. So it is a pretty good conformity as compared to the original CAD. So it's not deviated so much. Let's have a look at the entire tailpipe in detail. But what you can see on the screen, you may not be happy that, okay, the tailpipe now is been, there is a deviation over here. So let us have a look at the original CAD and understand what really has gone wrong. This is the original CAD. Let me zoom in and understand what is the difference between the tailpipes. So you can see that the gap between these two tailpipe was chewed up. This gap is pretty much critical for the vehicle thermal management team because the exhaust gases are going to be extremely hot and they're going to come at fairly greater velocity and they're going to interact with the wake region behind the vehicle. And modeling this gap between the tailpipe could be critical to understand what happens to the exhaust gases once they come out. Do they hit the, because of the wake region, do they rise up and hit the bumper and melt it, or what happens? So let us go ahead and understand and separate these two tailpipes. So this is left tailpipe 8. So I'm going to go ahead and create again a one group contact prevention for the tailpipe. Similarly, it's going to be 2 mm to resolve the gap between the tailpipe. Select left tailpipe 8 and click OK and execute. So before that, let me go ahead and open the scalar scene and keep it ready for us to understand once the wrapper is completed if the tailpipe problem has been resolved or not. Right click, execute. So once this is completed, what you can see that both the tailpipes are separate. So this marks the end of the first use of the solid wrapper feature, that is taking care of the deformities on the surfaces. The second feature which is important, the wrapper is used, as I mentioned, was to extract the fluid volume. And once this is completed, that is what we are going to have a look at. We're going to extract the fluid volume for this entire exhaust tailpipe using the wrapper. And this can be a very important thing for the underhood thermal management team or the vehicle thermal management team, because we want to model the exhaust fluids, which is the hottest gas in the entire simulation. And it's going to uh, it, it's going to flow to the exhaust line, heating it, and then the exhaust, it is modeled as a conjugate heat transfer analysis, and it's going to radiate heat to the surrounding components. So it is fairly important for us to model this exhaust gas, and that's what we are going to do next. Let's give it a couple of seconds. It's almost completed. It says surface wrapper completed, but right now what it is doing is it is remeshing the surface tessellation of the geometry. So um, there additionally, let me say that there is an excellent tutorial in the Star CCM Plus help manual. So you can anytime, it's an wrap operation of of a different manifold. It's completed. You can see both the tailpipes are separated right now, but there's an excellent tutorial in the help menu. In that you can go ahead and try it out. If you have any doubts or if you're not able to figure it out, please feel free to give me a call, or you can contact Yapus and we will be happy to help you out in any way. So as I said, the next step is to go ahead and extract the fluid volume. So I'm going to go ahead and create another operation of surface wrapper. So right click, new surface preparation and surface wrapper. I'm going to go ahead and select the entire exhaust geometry because it needs to be a watertight geometry, including the inlet and the outlets this time. Click on OK. Go ahead, to avoid confusion, I'm going to rename it fluid wrap, because this is the fluid volume which we are extracting. And I'm going to copy and paste the same name on the part which it will create. That is in the part T, you can see that there is one. Paste it. That's done. Now I'm going to go ahead and specify the base size for the particular operation, which is going to be 10 mm. This is the reference length for all other. And we are going to specify the minimum surface size, which is 10% of the base size. And the volume of interest is going to be seed point. So I'm going to select seed point as the volume of interest. create a new seed point over here, and let's orient the geometry perfectly. I'm going to zoom in and click on display tool point. So the seed point appears. So we will have to place 3 seed points, one in the front of the exhaust line, one in between the catalytic converters because it's a discontinued fluid, and one at the rear end. So I'm going to place one at the front. So one feature which you may find useful is the keyboard shortcuts for in Star CCM Plus. You can press T for top view, S for side view, and F for front view. So the front one seed point is already placed. I'm placing one at the rear. Let's confirm if it's placed inside in the top view. Just going to hit T. It wasn't. Okay. And the last seed point is going to be placed at the center of the catalytic converter. This is us specifying that we need to wrap in these particular locations. So the last seed point, and it's done. Hit on create, and we have the seed points ready. All the 3 points are ready. So the next step would be to close this and execute the fluid wrap operation. So this takes about 30 seconds to complete, and we will have the fluid wrap ready. Yep, that's completed, and we have extracted the fluid volume. So now let's have a look at the fluid volume. We have a separate scene that is 02, which is we have pre-created. This is the solid, which is transparent right now. So I'm going to go ahead and drop the fluid volume. And this is the extracted fluid volume. You can see that it has a very good conformity with the solid surface. Some places you may not be happy, like in between the catalytic converters or near the tailpipe over here, but you can always play with the settings, have a refinement there, or specify contact prevention and resolve these problems. So let us quickly have a look at how much it deviates from the solid geometry, the fluid volume. Let's remove the existing solid wrap over here. Previously, we had created a solid wrap for the deviation. Now we will have the fluid volume over here, and see how bad is the fluid volume compared to the solid geometry. How far is it deviating? So you can see that it is pretty good. It's not that bad. Everything is below 1 or 2 mm. Over here in between, as I said, between the catalytic converters, it may be a little bad. You can always refine it using a contact prevention also, as I have showed you. Now the question comes, why did we perform the wrap operations? As you had seen previously at the beginning, there were 4,000 pierced faces and other errors. So now let us have a look at the wrapped geometry and understand if we have bad quality CAD in the wrapped geometry. So I'm going to go ahead, right click on the wrap and repair this surface this time, not the original CAD, and understand how bad it is. Let us go ahead and quickly run diagnostic, and you can see that almost there are no bad. It's running right now. Just give it a second. You can see that almost there are no bad surfaces present. Everything is clean. So it says 00. Give it a couple of seconds to complete. Yep, there are no bad surfaces, so we can move ahead with meshing. So let us have also quickly see if there are bad surfaces in the fluid volume wrap. We can see that once this is complete, there are no errors in this particular part. And this was the advantage of having the wrap feature shown today, that all the deformities, that is maybe thousands of deformities, are taken care of just in a couple of minutes. Now I'm going to hand it over to Daniel Steen, who is with us from Siemens today. He's an expert with a lot of years of experience in the vehicle thermal management industry. So over to you, Daniel.
Hi, Dan. Your audio is on mute. Could you please unmute that? Thank you. Hi, Dan. Yeah, your audio is still on mute. Just on the GoToMeeting within the audio section, please unmute yourself. Still can't hear you.
Hi, thank you.
Perfect. Go ahead.
Can you see my screen now?
Yeah, we can see your screen.
Okay, great. So thank you, everybody. And I just want to walk through really quickly. Thanks for demonstrating that. And I just want to walk through really quickly what some other customers have been able to do with Simcenter Star CCM Plus. So in general, a lot of the customers who use Simcenter Star CCM Plus use it for a lot of the capacity that we were discussing today. So the ability to handle data management, to handle these really complicated geometries in a really quick and effective way, and being able to actually integrate all that knowledge and material and data very quickly into a simulation, which begs the question, how long does this step take for you and the folks that you work with? So for some customers we've worked with, it's actually taken weeks to prepare these kinds of simulations. And thanks to Simcenter Star CCM Plus, we've actually been able to get that down to just a couple of days. And this was the case for General Motors. We worked with their thermal management group to reduce the model build time by 85%. It was a 7-week process that we got down to about 6 or 7 days of total turnaround time. And what enabled this was the ability to easily handle all of this complex geometry, and without the need to manually clean up an entire vehicle's worth of surfaces and parts and things like that. Thanks to the surface wrapper and thanks to filters and handling like that, we're able to much more rapidly bring parts in and just immediately start using them to perform really complex simulations. Using a template sim file also helped speed the process and reduced user error. There's less that the user has to set up, and therefore results are more consistent. And ultimately, by pairing this with Teamcenter and using TC Viz Mockup to do further organization and help coordinate iterations on their designs and minor changes to explore changes to individual components or sections of the vehicle, this basically has increased their turnaround time almost an order of magnitude. Now, in regards to using Simcenter Star CCM Plus, it's actually very cool because you can use it for a whole different suite of multi-physics. Today, we discussed a lot having to do with thermal, so convective, radiative, and conductive heat transfer. But what if you needed to add more to that? What if you needed to add elements of, if you wanted to use it for elements of combustion, or you wanted to include particulates or multi-phase flow or things of that nature, or you want to model a coolant loop, an oil loop, an air loop, Star CCM Plus gives you the flexibility to actually do a lot of this. So a lot of customers who have unique solutions to complex problems need to be able to simulate that. So the question we pose is, what makes your products unique, and how do you go about modeling that today? One example here is CNH Industrial, who have used Simcenter Star CCM Plus pretty heavily for full vehicle system simulations. A lot of it having to do with like particulate spray and things like that. But they also have to deal with thermal management problems, and they have to do it in really complex environments where there's dust, where there's ingestion of elements that are getting sprayed out of the vehicle. There's emissions concerns to worry about. There's a lot of this that really interplays in a complex way that Simcenter Star CCM Plus provides a unified platform for them to investigate those kinds of problems. Indesa is a engineering and consultant firm, and they have a strong history of using Simcenter Star CCM Plus with 1D simulations. The idea being that you can use a 1D model to model the complex behavior of what's happening in an engine, or even the engine control module, or even really complex architectures like hybrid drivetrains. And they can use that to model how much heat the engine is generating, how much heat is getting dumped into the radiator coolant loop. All of these things can basically be modeled by the 1D system, and in turn, the 1D system can take in input from the 3D model. And so by combining this, you basically get the best of both worlds. You get the complex 3D aspects of doing a full CFD model in Simcenter Star CCM Plus, as well as the really nuanced 1D modeling of your drivetrain and other systems. Mitsubishi have actually gone a little bit further. They use this with this sort of 1D, 3D coupling for plug-in hybrid electric vehicles, and they even go all the way into working with the cabin in some instances. With future vehicle architectures like electric vehicles being much more sensitive to small temperature differences, cabin modeling can become more and more impactful in the performance of your drivetrain and become a bigger part of the thermal management equation. So being able to model the really complex systems of the drivetrain, the HVAC, the cabin, the exterior of the vehicle, the underside of the vehicle, basically lets you encapsulate the entire performance of the system. And this is essentially what Mitsubishi and Endesa have done with 1D, 3D coupling. So the rapid turnaround is what Simcenter Star CCM Plus has been built on top of. And the idea is you want to be able to do the CAD and simulation test as quickly as possible. You want to be able to make that simulation, learn from it, make a modification to your design, and very quickly go through that process before your program deadline, such that by the time you're actually cutting sheet metal, you're really just doing verification, validation of your models. You're not hitting new surprises that require you to start building even more parts and extend your program deadline. So the question is, how much time do you guys actually spend improving your designs versus simply trying to confirm that they work okay? And can Simcenter Star CCM Plus help? So this is where Daimler has been using Simcenter Star CCM Plus heavily with the help of our services department. Our engineering services group, excuse me. They use Star CCM Plus for these really complex models, and they do it very, very quickly. And to the point where they've been able to replace a lot of testing. So even as far back as 2007, they had a lot of hardware test phases. So you could see that in the beginning, they had sort of a whole bunch of different hardware test phases with simulation supporting those test phases. And then they moved to where they actually had full digital prototyping for roughly the first half of their testing. And then in 2014, they're almost entirely a digital testing house where really the only physical testing they do is more for validation of the model and maybe some special cases, but primarily they are gone completely to digital test. And this has been with the help of Simcenter Star CCM Plus. And yeah, that's all I have. Back to you.
Thank you, Daniel, for the overview of Star CCM Plus.